Hello everyone, welcome to my video. I am Mo. I will be discussing today my projects that I did in my university and my what I found, what I discovered and the challenges that I have encountered. So please stay tuned and I hope you enjoy the video. So my project is titled Deep Learning Based Vehicle Damage Detection and Repair Cost Estimation for Insurance Automation. So this is an automation project to understand to solve a solution. So the problem starts with the current systems here in Malaysia is that the when the car gets in an accident, the car will goes to the repair workshop, and then the insurance will send an adjuster, we call it here, that will create a cost estimation, and then with that adjuster a cost estimation report, and then the insurance will also send another adjuster to verify that initial cost estimation. Once the verification is approved, then only the money is released to start the repair. Now this process takes a long time, and sometimes it could take from 7 to 14 days or even longer during festive seasons. And that's the first issue. The second issue is that there are sometimes some cases where the adjusters will collude with the workshop to overestimate the price, and then they will pocket the difference, so which leads to some fraud. So now the current digital tools cannot process these visual evidence and generate. So current digital tools cannot process these claims, this visual evidence, and or automated cost estimates. There's not many current systems that does that, and my goal is to build a system to at least give a benchmark or find out if it's possible with damage detection AIs. So my goal is to remove that subjective manual process to an object detection AI driven and cost estimation. So the question is, can an AI system reliably detect vehicle damage and generate an accurate cost estimate report for the images from the images alone? So moving on to the project overview, I created I initially I went and researched about this topic, and I identified some research gap by reading different literature, and I found out that the damage assessment itself is manual, and it has some limitations, some inefficiencies, and bias, and which justified the reason for the AI based automation. So, my goal with that, from reading those papers, was to build multiple different AI models and build a system that trains multiple different AI models. These are YOLOv8, YOLOv8, YOLOv11, MobileNet, and faster RNN on a unified data set that is an open source, so that it gives a baseline to how the models behave in when it comes to a certain number of classes and so on. And when it comes to and then the automate and also automate the cost estimation part of it by using a rule based by using a transparent design to just understand how the cost is broken down, so that it's easily tweaked. And my currency of choice was the Malaysian ringgit to generate insurance quotations. Now, when I validated the system, I validated based on the accuracy, the consistency, the efficiency, and also some qualitative evaluation, such as interpretability of the cost and also the usability of the system overall. So, moving on to what the literature tells us, based on what I have reviewed, first is that there is limited real time adaptability. Most of the research stops at the research phase. There is no mention of it being in production or at least being pilot tested. Second observation is that there is an over reliance on annotated data sets. Many of these researchers tend to choose data sets that are they cater that data sets to their model of choice, and as a result, the model performs splendidly, while because their data sets is too clean. So it's not the model tend to not generalize that well, and this will cost. And then another thing is most of my findings is that a lot of models have insufficiencies in handling minor damage such as scratches or cracks, and I wanted to find if it's possible to try different models to evaluate if that's the case. Now, data imbalance and bias, that's as I mentioned before, sometimes they would create models which have limited, very little number of classes so that the performance of the model increase. Now, explainability and trustworthiness, that is mostly to regarding uh, the cost estimation. There are some cases where they use convolutional neural network or CNN and linear regression, which tend to have a gray zone on how the cost is broken down. And furthermore, there's a lack of unified benchmark data sets. Most of these data sets are proprietary and not shared for us, the readers, to evaluate them and find out if the model really performs as they claim it is. Now, second and lastly, scalability and regional adaptability. Most of their training is they proposed is just for their region, for their city, and one price range. I wanted to try out different places, different locations, different price range, and I proposed a certain solution for that. Now, moving on to what the literature tells us again, in terms of the model detection achieved, a lot of research says that it achieved high accuracy. Particularly, we can see YOLO V5 and YOLO V8 achieved 87% MAP score on the Tertestia dataset by Perez Zarte. And MobileNet V2 achieved 89.2 classification accuracy for mobile deployment. Now, please don't be fooled by this amazing results of accuracy. When I read through the paper again and again, I noticed that they tend to limit it to three classes, which is severe, minor, intermediate, and severe, and that is all their classes of their data set. My case, I wanted to explore if MobileNet V2 can handle 11 classes, and if it does, we can increase the classes so furthermore. Now, FRCNN, some research said that it performs excellently with fine-grained detection. So that is something that I wanted to explore and see if it's possible to achieve that. And an honorable mention, which is visual vision transformers, they achieved an accurate segmentation with in cluttered backgrounds, but vision transformers required a very big data set, and a lot of tokens, a lot of very expensive hardware. So therefore, I did not explore it in my case. Moving on to cost estimation methods, I also explored rule-based systems, which is just a lookup table, and then it pulls the information into that. There is a lot of research about that. There is some cases with regression models with convolutional neural network together with gradient boosting. I kind of strayed away from that because it's not so explainable, and for compliance cases, it's better not to. When it comes to money, I prefer to a more explainable cost breakdown. Now, for hybrid approaches, I chose my solution of choice was a hybrid approach, which takes in the severity based multipliers, and then I use a structured pricing. It's a predefined pricing for this phase, and then I multiply it with the regional multiplier and the severity and tax as well. So it's more easily broken down. I will discuss that in the demo in the next video. Moving on to the research gap and my contribution. So the gap is that complex heavy models tend to dominate the research. They like to go with the strongest, biggest model. My choice is that I wanted to explore a diverse range of models and different deployment possibilities, just to see if it is possible to try out what works, what's the highest performance, and what's the medium performance that is a good trade off. Now, the assumed trade off is that accuracy and speed and explainability, then also academic prototypes rarely deployment ready. So my contribution is that I created a systemic. I compared those five models, different lightweight architecture, and I also proved that lightweight compressed architectures, such as the ones with 2.6 million parameters, achieved best quality, best accuracy through its extended training. And then the second one is also with a transparent cost estimation, which enables some form of production deployment. And when I deployed it in production, it did achieve of 85 to 95 millisecond end-to-end accuracy. Next, the model or methodology itself. This is a very top view methodology. I took the data set. It's pre-annotated, but I cleaned it. I removed big pictures or low resolution pictures that do not meet my criteria, and blurry pictures as well. And I once I've done with the training with the cleaning, I moved on to training. I trained it based on the five models, but for each model, I will train it and see its performance, and if there are any chances for me to improve that performance, and see how the model behavior after inserting the data set. And once I've completed the five model training, I would move on to evaluation of the final and evaluate the chosen model, the best performing model. Once I evaluate that, then I would deploy it together with the cost estimation. So about the data set, it's car damage detection, car DD data set. It's an open source data set, easily be foundable in Google. And the initial size of it is 10,247, but then after cleaning, it becomes 9,856 high resolution images. Then I split it into 70, 20, 10. 70 for training data, and 20 for evaluation, and 10 for testing. And it's already annotated with 11 classes. And what I did was I changed the annotation format to match the models that I would be training. And further, I cleaned it as well. And then I split the data set. It was already pre-split, but then I merged it again and did stratified sampling just for peace of mind. So my models of choice was YOLO V5, YOLO V8, YOLO V11, and MobileNet and faster RCNN. For YOLO V5, I wanted a baseline of the YOLO family. It's very stable, and there's a lot of good talk. So I wanted to find out if how good it performs, and then I would go further. So I tried out YOLO V8 because it has a bigger parameters, and also based on my architectural observation, I noticed that it has an anchor-free detection. and C2F modules. I wanted to explore how good is that, how much of a performance boost, and then I also wanted to check out YOLO V11N with 2.6 million parameters. I wanted to find out if a smaller, streamlined model with an improved architecture can perform better. The advantage of this is that it has a streamlined backbone. And further, MobileNet V2 is because I've seen many papers that claim that it's edge deployable. So I wanted to see if it performs well in my training and my testing, then perhaps deploying it on a smartphone and checking if it's a feasible approach. Now, for FRCNN, it's a two-stage detector. So I wanted to find out how a big model set with 441 million parameters can perform. So I its architecture is high precision and regional proposal network (RPN). Now it behaves differently, and then I will explain how different it behaves later on in my challenges. Now, further on, as a system architecture itself, I created a simple UI as seen here, which is the input, and then which is a Gradio interface. And once the Gradio interface takes the image, first it checks its if it's a JPEG or PNG, or if it's a different format, it will convert it back to JPEG, convert it back to PNG, and then it will feed it to the model. Now, I tested across all of the five models, and for my final deployment that I used for demo, I've used YOLO V11 for my final deployment. And then once the model observes and finds the damage classes, then it will output a data frame, and that data frame is then taken to the cost estimation module, where it will take in the damage part and its severity from the data frame, and then it will do the calculation. Once the calculation is complete, and then it will give a cost estimation report. Now, for my training, for my YOLO V5 and YOLO V8 and 11 for the YOLO family, I initially set to 120 epochs, but early stopping came in around 50. Around 50. Then I started observing its behavior. Now, for YOLO V5, I noticed that it was stabilizing, so that means the model has trained, and further training was not that necessary. And YOLO V8, it proposed a better when I compared the box loss across them. I noticed that the performance is slightly better than the YOLO V5, but it's also stabilized, so it didn't need further training. But then when I observed YOLO V11, I noticed that it could lead to better training, a better longer duration. So I removed the early stopping, or I increased the patience for the early stopping, which caused it to train further to all the way to 120. And by increasing the patience, it greatly impacted the performance of the model. And once it reached 120, as you can see, the curve stabilized. So that means it's possible. It's The training is complete. FRCNN was my champion model. It performed the best. It achieved zero point 0.8 MAP score, which is 80% MAP score. That means it represented all the classes really well. It detected all the damages that I tested on it. Now, further on for my training and evaluation, I used precision. Why I chose precision? Because I wanted to reduce the false alarms and unnecessary repair estimates. And for recall, I wanted to find out. I wanted to ensure there's no damage is missed, and preventing underestimated costs. And F1 score, I used it as a general to compare all the models, and further on the MAP score, just to compare how each model performs across different classes. Now, the performance for each model, looking at the models, my best performing model was the YOLO V11, as it achieved 66% MAP score. That means it kind of it picked up most of the fine grained, but not all of them. It can do better. And further on is my precision did well at 75, and the recall was all right, and F1 score achieved a respectable 67.7. Moving on to my best model is my faster RCNN, and it achieved 90.93 of recall, which allowed me. Now this is with the default setting of FRCNN. I played around with it and it became better. This is the now for the precision was also respectable at 63, but it is possible to tune the precision and recall by playing with the threshold. So for this model case, and it can greatly increase, and but at the cost of reducing recall. Now for the F1 score, it performed at 75%, which is a really good performance, clearly 76. And finally, for the MAP score was 41%. But don't be fooled, this is ranges from different threshold. This is the default threshold because everything here is running on the default threshold. I later on tweaked the MAP score for FRCNN to improve it. Now, moving on to Mobile Net V2, I will discuss its performance. So the toughest challenge for that I came across first is the Mobile Net V2 is that there was an architectural capacity limitation, and it achieved initially 23.9 despite optimization training, despite my attempts to optimization, it plateaued at 5, at epoch 5 or below epoch 5 in this case. And I tried different methods, so warm restarts. I also adjusted my data set to tweak it more, but of course this is not the best approach to increase the model performance, but this is as far as I managed to get it. And from that, I learned a lesson that depth-wise separable convolution sacrifice too much accuracy. That's the first observation. And also, I discovered that a bigger parameters like mobile net v2 performed worse than a smaller parameter model such as 2.6 million in YOLO v11. Now, also the second challenge was the threshold for FRCNN. I needed to find out what is the optimal threshold. So my findings is that I discussed with insurance providers different image samples and told them which is the most cases that they would like to observe, and then I came across that it's better to I increased the threshold to 0.7, and it performed excellently. And also the second lesson is Coco annotation. Don't transfer to sparse detection tasks, and also it requires application specific optimization. Now further on, I also discovered that the architecture design of the system itself is what influences the model's detection over just the parameters, over how many parameters. And as also to conclude it, not all parameters are equal. Sometimes better performing architectures do well. And next is the threshold optimization. As I mentioned before, initially it performed at 10%. And then when I optimized it afterwards, the F1 score jumped to 75%. Now, evaluation methodology is critical for as the model architecture. And also the threshold itself generated, for example, 28,000 at zero point 0.5 threshold. But then after over the detection is only for 986, producing 97 false positives. Then when I changed it to zero point 0.7 threshold, it filtered out and giving me preserving the recall at 93.7, almost 94%. Further on, there are some limitations of the dataset. First off is the granularity of the dataset. I trained it on 11 classes such as dance, scratch, crack, but of course in real world we have hood, door, bumper, and so on. There is more classes. The reason why is because one, the dataset itself is already annotated. I wanted to use my time learning different model training such as TensorFlow or PyTorch and different languages for how to interpret the models and their behavior. And the data sets itself was already annotated. In the future, I would annotate it again. And then the second thing is static pricing and dynamic market. My pricing is an average of what is the local cars here made in Malaysia. My goal is to make it more dynamic so that it responds to different cars. For example, here generic vehicle costs, and also account for tariffs or inflation in price. Now, lastly, is I validated it. Although I did give it to a few insurance agents, but I would have liked it more into to explore a whole deployment as a pilot testing, just to see how it performs in the real world with different types of users. My user base was around 20 users of professionals, but I wanted to further try it out in the future. Now, key contributions was more parameters equals to better accuracy. That I challenged that idea as my YOLO V11 with 2.6 million parameters performed better than the YOLO V8 with 11.2 by 8.5 MAP through extended training. And also I established some architecture design means better than the parameter count, and bridge the academic prototypes with production deployment. I did make a prototype that was deployed, and I did show it to a few insurance agents, and they tried it out with their own data, and it did perform well. So it's good enough to move on. So my YOLO V11 performed. Well, I noticed that it performs well in a client server architecture, and this would work in client server setup where a user can take a picture and then it will send it to the server, process it, and then will send back, as we would see later in the demo. And FRCNN performs better as later on for batch processing, or yes, it performs more in batch processing, and it also overlooks the fine grained, but it takes a lot of computational power to inference to generate a simple damage detection. So it's better to do it over batches. Now, further on, the production ready system, if we were to deploy it, I would recommend a YOLO V11 as the client server. And then that will be the first adjuster. And then the second adjuster would be the FRCNN as the expert to validate the YOLO output. And then a final step is a human to annotate and say that, oh, yeah, this is the detection, or adjust it again. Finally, for future recommendation, I would say first is re-annotation, as I suggested, increase the number of classes, and this will greatly reduce the cost estimation error, because different classes we will have more granularity with 10 to 15% improvement to 10-15% error rate. Vehicle specific pricing, I would have loved to add a drop down to select a model, and then it will adjust based on the car model. For example, if it chooses a Toyota, then it will choose a Toyota Yaris, then it will select that price. And finally, the Ansible detection, as I suggested earlier, by combining YOLOv11 and FRCNN and real world deployment just to pilot test it further. And yeah, so that's about it. Thank you for coming to watching this video, and stay tuned for the demo.